Hello everyone and welcome to Nano. My name is Carla and I'm a medicinal chemist at Nano. And I'd like to introduce our special guest today. This is Greg Critchlow. He's at the RCSB Protein Data Bank.
Oh, well, thank you very much for having me, Carla. This year marks the 50th anniversary of the founding of the Protein Data Bank. In celebration and recognition of this, we want to discuss with Nanome some of the protein structures that have appeared in the Protein Data Bank over the past 5 decades that have led to understanding of pharmaceuticals and of pharmaceutical development. And this structure here, you see in the timeline highlighting the 70s, this was deposited in the early 70s. It's actually hemoglobin. You have 4 chains here, and this structure shows how the chains can communicate. How when oxygen binds to one, will bind over this iron ion, it causes this chain to communicate with neighboring chains in the protein, and it changes their affinity for oxygen so that all 4 chains can bind oxygen essentially together and release oxygen together. Now, what is this molecule here? You probably recognize it.
Aspirin, yeah. Wow.
So here in this case we have, this is a protein called COX-1 for cyclooxygenase 1, which is one of the targets of aspirin, and a related cousin of aspirin called salicylic acid binds to that also. And what you see here, actually, this little thing here is a salicylic acid molecule. Aspirin is actually acetyl salicylic acid, which is this salicylic acid, but it has a few extra atoms appended onto this oxygen here. Depositors who determined the structure, they actually incubated this protein. They mixed this protein with aspirin. A derivative of aspirin, bromocetylsalicylic acid, is showing how aspirin works, how the aspirin will react. These represent the extra atoms that are part of the aspirin molecule. That reacts with the enzyme, and the aspirin is essentially cleaved, in essence, cleaved into 2 pieces, and these atoms are then end up covalently bonded to this oxygen of this amino acid called serine, and what is left is a salicylic acid molecule, which remains bound in the active site. So this is showing how aspirin actually inhibits this pro-inflammatory enzymes. That's why aspirin has anti-inflammatory activity. So this enzyme on the right is actually a target of beta-lactam antibiotics, the family that includes penicillin, which targets the active site serine residue. This also happens to be a serine amino acid that reacts with the antibiotic.
Beta-lactam, right?
And it hydrolyzes, it's also a hydrolysis reaction, hydrolyzes the antibiotic and eventually gets released from the enzyme by water molecules, why it's called hydrolysis. You see the water molecules come in, react with it, and then will release the antibiotic. However, the hydrolysis is very slow. And it is so slow that by the time it happens, the bacteria is dead. So this penicillin binding protein, and it's actually involved in building the cell wall of the bacteria. It cannot build the cell wall as long as this antibiotic is bound to it. And here, on the left here, you have an enzyme that actually causes resistance to antibiotics.
Wow.
So in bacteria that are resistant to a particular antibiotic, in the case of beta-lactam antibiotics, it's usually because they produce this enzyme called a beta-lactamase. That destroys the antibiotic. The antibiotic will bind to the active site of the enzyme of this beta-lactamase just like it binds to the active site of the penicillin binding protein. But the difference is, in the beta-lactamase, the water molecule that releases the antibiotic can do that much more easily and much faster.
Yeah.
So this actually gets hydrolyzed very quickly So instead of the enzyme being inhibited, the antibiotic is just turned over and is destroyed. Once it's hydrolyzed, it's destroyed. It can't bind to the penicillin binding protein. In this active site, you have again, an active site catalytic serine amino acid here. And this oxygen reacts with this inhibitor. Now, this is an inhibitor called clavulanic acid, or clavulanate, which is actually used in a drug called Augmentin, which is a combination of clavulanate and amoxicillin. So that's designed specifically for resistant bacteria that make a beta-lactamase like this. The clavulanate will inhibit the beta-lactamase, and that allows the amoxicillin to be free for reaction with the penicillin binding protein over there. Here's another example of structure-based drug design. Now, the last class of drugs we talked about were antivirals.
Case, right.
Yes. Here, this is an oncological case. This is an anti-cancer drug called imatinib. And now this was deposited, this deposited in 2000. So now we're fast forwarding to the 2000s. This drug binds in the active site of BCR-ABL, which is a mutant enzyme produced in certain patients who have a particular form of leukemia, which is a type of blood-borne cancer. And in those specific patients who produce this mutant enzyme, this kinase, the enzymatic activity of this enzyme goes unchecked.
Yeah,
and it keeps being active when in a normal person, it will be active at times and then stop, active at times and stop. In these patients, this enzyme keeps going. So cells keep growing. Yeah. So you have an overproduction of leukocytes, as I said, it's a blood-borne cancer. So this molecule comes in and inhibits the enzyme by, again, binding into this active site here. And this structure shows how this was able to be designed to fit directly into this active site and, in essence, clog the enzyme so that it cannot bind its substrates, natural substrates that it wants to bind, and therefore cannot be active. So therefore, this stops it from being active, and it stops the cells from growing out of control. This was deposited in 2019, and this is the structure of a protein called K-Ras, which is implicated in many cancers.
Yeah, quite a few.
And for a long time, there were many medicinal chemists who were thinking that this enzyme is undruggable because scientists were not able to come up with a drug to inhibit this enzyme. But if someone could, it would be a great boon to oncology research because there are many cancers that are driven by mutant K-Ras enzymes. And this drug represents the first FDA-approved drug to target a K-Ras mutant enzyme, which was approved in May this year, May of 2021, approved by the US FDA. Yes, and this drug, sotorasib, binds to the glycine 12 to cysteine mutant, G12C mutant of human K-Ras. So in this case, the active site amino acid is a cysteine. Cysteine has a sulfur atom. That reacts with this part of the inhibitor.
Warhead.
And yes, what medicinal chemists call the warhead of the inhibitor. That attacks the enzyme and latches on permanently to the enzyme, permanently disabling it.
Let's take another look at that with a different representation in nano. This is the surface representation that kind of shows pockets, so you can see.
And this is right, and this is really a great representation to show because you actually can see here the GDP here. You're getting very close to this inhibitor that's in this coming out of this side of the pocket that's bound to the cysteine.
Well, thank you, Greg. This was really fascinating, and it's amazing how much the RCSB has contributed to drug development over the years, and we have so much to look forward to in the
Yes,
future.
right,
It's
with more than 180,000 structures of
structures.
biomacromolecules that have been deposited over the past 50 years, which is providing a wealth of information for pharmaceutical companies to do designs such as this,
A lot of insight,
and to
definitely.
then test their designs.
It's really a very beautiful structure.
This
It's wonderful to be able to be part of this journey with Nanome's technology, which really allows for some incredible visualization of all of these interactions and really helping med chemists and structural biologists design some new molecules. So thank you
Yes,
very much for
yes.
joining us today.
Well, thank you
Really
for
appreciate
having me. I
having you.
appreciate it.